This recording is to help you with lesson 2.05, the fundamental theorem of algebra. Alright, to start things out, let's find all the zeros of the function and write the polynomial as a product of their linear factors. Alright, remember we can find all the possible zeros by doing p plus or minus p over q, where p is all your factors of your constant, and q is all your factors of your leading coefficient, in this case 1. So all my possible zeros are plus or minus 1, 5, 25, and 125. Now from here, you're just going to have to use synthetic division and hope you have the luck of the draw when you're choosing your numbers, because we are looking for a remainder of 0. Now in this one, negative 5 is going to work. So if we run through our synthetic division, I get the resulting polynomial here of t squared minus 8t plus 25. All right. Once you have that resulting polynomial, remember you can either try to factor it or use the quadratic formula. Now on this one, we cannot actually factor that, so we do have to use the quadratic formula, and when we do so, notice that we get a negative value underneath my square root sign. Okay, so we will get 8 plus or minus, I believe it is 6i all over 2. And we can simplify the 8, 6, and 2 to be 4 plus or minus 3i. And that's what they have right there. Okay, so my zeros are negative 5, 4 plus 3i, and 4 minus 3i. Now, how do we write those as linear pairs? Well, we have to solve for t in each case. Well, if t equals negative 5, then we have to add 5 to both sides to get t plus 5. So there's one pair. If t equals 4 plus 3i, we would have to subtract 4 and subtract 3i. There's a second pair. If t equals 4 minus 3i, we would have to subtract 4, but add 3i this time. So there's the third linear pair. And that's what we can see written in the very last step. All right, for the next one, it says find a polynomial function with integer coefficients that have the given zeros. So here we're going to kind of work backwards. We have x minus 5 and x minus 5. So I know that's the same thing as saying x plus 5 times x plus 5. I also have 1 plus the square root of 3i. So that's x equals 1 plus the square root of 3i. Remember, the conjugate is also a 0, so I'd have 1 minus the square root of 3i also. Now, to get those into linear pairs, remember we'd have to subtract 1 and subtract the square root of 3i. And then we have to subtract 1 but add the square root of 3i. Okay, now we're just going to FOIL them. I'm going to FOIL them separately. In the first case, I get x squared plus 10x plus 25. And the second one, I have to use the distributive property 3 times. So I get x squared minus x plus x square root 3i. I'd have negative x plus 1 minus square root of 3i. Negative x square root 3i plus square root 3i minus 9i squared. Okay, let's kind of combine like terms in the second mess here. I have x squared and no other x squares to join that with. Okay, here's a minus x, here's a minus x, and that's all I see, so I can have minus 2x. see. That should be a 3, not a 9. That's what my problem was. Okay. I'm also still looking for like terms. So I have a plus x square root 3I minus x square root 3I. So those cancel each other out. I have a negative square root 3I and a positive square root 3I. Those cancel each other out. Remember, I squared is the same thing as negative 1. So really, I have a plus 3 at the end here. So plus 1 plus 3 is a plus 4. So that whole mess simplifies to x squared minus 2x plus 4. And then I have to FOIL and distribute again. So that gives me x to the 4th minus 2x cubed plus 4x squared plus 10x cubed minus 20x squared plus 40x plus 25x squared minus 50x plus 100. All right, let's combine like terms. X to the 4th has nothing to combine with. Let's look for my x cubed next. I have a negative 2x cubed plus 10x cubed. So that is a positive 8x cubed. Let's turn to the x squared. So 4x squared minus 20 plus 25 is 9. Then we can do the x's. So 40x minus 50x is negative 10x. And I have that plus 100 at the end, which matches up to the answer that was given there. So that's good. All right. Use the given 0 to find all the remaining zeros of the function. All right, if 5i is a 0, I can use synthetic division here. So I have 2, 3, 50, and 75. So let's start this. 2 times 5i is 10i. So I have 3 plus 10i times 5i. So 5i times 3 is 15i. 5i times 10i is 50i squared. Now 50i squared is the same thing as negative 50. When I add these, the 50s cancel. I'm left with 15i. 15 times 5 is 75. I times I is I squared. So I have 75i squared, which is the same thing as negative 75. So I do get 0 there. Good. So now I can take this answer and use synthetic division again. So I'm just going to replace it there. And if I know 5i is a 0, negative 5i is also a 0. So I'm going to go through synthetic division again. 2 times negative 5i is negative 10i. Then I'm left with just 3, and I get negative 15i and 0. This was much easier. So then I'm left with 2x plus 3, and I can easily solve 2x plus 3 by subtracting 3 and dividing by 2. So x equals negative 3 halves. So the 3 zeros are negative 3 halves and plus or minus 5i. Now, if that was confusing, there is another way that you can do this. All right, you can say that I have x plus 5i and x minus 5i. So let's FOIL that and see what I get. Well, that's x squared, the middles drop out, minus 25i squared. Remember, I squared is the same thing as negative 1. So really I have x squared plus 25. And then I can actually use long division to help me solve. And that's what we did right here. So if you prefer that method, you can do that also and use long division to get your answer. And notice that you do get the 2x plus 3. So again, you just have to subtract 3 and divide by 2. All right, the last one you're just going to do on your calculator. It says, use the root or zero feature of a graphing utility to approximate the zeros of a function. All you're going to do is just type this into your calculator and get the decimal answers. It says, determine one of the exact zeros, use synthetic division to verify your results. So what we could do is, we notice that on our graph it looks like 1 and 2 are exact zeros. If we do that, we can use synthetic division to see that yes, 1 and 2 actually do give us a remainder of 0. And then we can take the resulting polynomial, which was x squared plus 6x plus 11, and you can use the quadratic formula to solve from there.